All right, here is section 3.2. Now we're going to take our exponential functions and kind of do some modeling with it. We want to be able to use exponential growth, decay, and regression to model real-life problems. What you see here on this first slide is just sort of a setup for the formula for an exponential function involving population. It says, suppose that a population is changing at a constant percentage rate r, where r is the percentage rate of change expressed in decimal form. Then the population follows the pattern shown, and you can see the pattern. The population is an exponential function of time. So if we look at the next slide, here's our formula. Okay, P of t equals P naught times the quantity 1 plus r raised to the t power. P naught is the initial population, r is expressed as a decimal, and t is time in years. Okay? If r is greater than 0, then P of t is an exponential growth function, and its growth factor is the base of the exponential function 1 plus r. On the other hand, if r is less than 0, which means the base 1 plus r would be less than 1, P of t is an exponential decay function, and 1 plus r is the decay factor for the population. So if you look at the first example, they want you to tell whether the population model is an exponential growth or decay. Find the constant percentage rate of growth or decay. So if I look at part A, the only thing I'm worried about is that right there. So 1 plus r, 1 plus r equals 1.0064. Okay, so if I subtract 1, I get 0.0064. Okay, now that number is greater than 0. All right, so since that number is greater than 0, we have growth. Okay, now the growth rate. Okay, the growth rate is 0.64%. Okay. Now, for part B, again, all I care about here is the base. So it's 0.9858. Subtract 1, and what I get now is I get negative 0.0142. Now that, that is less than 0. Okay, negative number less than 0. So we have a decay. Okay, we have a decay. Now, that R, the decay rate is 1.42% decay rate. So it's part A, we're growing at a 0.64% rate, and part B, we're decaying at a 1.42% rate. When you find those rates, guys, make sure that you clearly state whether it's a growth rate or a decay rate. Okay, now it says determine the exponential function with initial value 12 increasing at a rate of 8% per year. Okay, initial value, that's P naught, that's 12. Okay, our rate is 8%, but we can write that as 0.08. Okay, I have a hard time making decimal points on this stupid thing. Okay, so P of t, we just apply our formula from the couple slides ago. So it's 12 times 1 plus 0.08 to the t power. Now, we can simplify what's inside. Okay, we could just do that. All right, so 12 times 1.08 to the t power would be our answer. It's very simple when you do that. Very simple. All right. All right, exponential growth and decay models. We talked a little bit about growth and decay in 3.1. They're used for populations of animals, bacteria, even radioactive atoms. We're not going to get into radioactive decay, I don't think. So let's take a look. I mean, this kind of explains it a little bit, but let's take a look. All right. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. Okay. All right. So after 1 hour, okay, after 1 hour, it doubles every hour. So we take our initial value, 100, times 2, because it's doubling, that means the base is 2. 100 times 2 to the first, that's 200. Okay? Come on, you stupid thing, right. After 2 hours, okay, now our starting value is 200 times 2 to the second. Okay? Remember, t, the time, in hours in this case, is the exponent. Okay? Actually, it's 100, excuse me. Whoops. Okay? So that gives me 400. After 3 hours, 100 times 2 to the third. That's 800. Okay? So here's what's happening. P of t equals 100. Whoops. 100 times 2 to the t power. All right? Now, I would probably tell you to probably graph this. So I would graph that in your calculator. Okay? All right? And then it says predict when the number of bacteria will be 350,000. So you want to graph the exponential function. Okay? And then graph, okay, y equals 350,000. Okay, now, I don't know how you're going to do that, but it's a horizontal line. Okay, it's a horizontal line. What you want to do is find the point of intersection of those two graphs. Okay? All right. So, what you're going to find, and you can work this out in your calculator, is it takes about 11.77 hours to get to 350,000 bacteria. Okay? So, that's the way I would do it. I would find the exponential function, find the growth function, graph it, and then graph whatever number you're expecting it to, you want it to be, graph that horizontal line, and then find the point of intersection of the two. Skip a couple slides. All right. Using regression. Okay, this is, remember our lin reg, quad reg, cubic reg, and all that stuff? Well, we can also do exponential reg. Okay? So far, our models have been given to us or developed algebraically. We now use exponential and, well, we're not going to use logistic regression to build models from population data. Due to the post-World War II baby boom and other factors, exponential growth is not a perfect model for the U.S. population. It does, however, provide a means to make approximate predictions as illustrated in Example 6. Segue, Example 6. Look at that. Let me make that bigger. Use the 1900 to 2000 data in Table 3.9 in exponential regression to predict the U.S. population for 2007. Compare the result with the listed value for 2007. So, here's your L1, here's your L2. Now, look at the years. Look at the years. For me, I would go 0, 10, 20, 30, and so on down the line. Do not stop right there. Stop right there. Don't put 2007 in. Okay? That 2007 is there as a reference point. Okay? So, you put in your L1 and L2. Boy, I tell you what. I cannot write with this darn thing. Enter. This is like using my smartboard. L1 and L2. Now, use EXP reg, which I believe is option 0 on your calculator. So when you go to stat and then calc, and then you got to arrow all the way down, I think. Okay? So in this case, all right, in this case, your model, okay, is going to be P of T equals 80.55. Oh, you know what? This thing is super long. Let's write it down here. So P of T equals 80.5514 times 1.01289 to the T power. Okay? Now, in 2007, how many years have elapsed since 1900? 107 years. So now, plug 107 in for T. Okay? So you're going to plug 107 in here for T. Now you put that in your calculator, put that whole function in your calculator, all right, and then find out what that actually is. So I believe, okay, I believe this gets you 317.1 million. Okay? Now, compare that with what they listed. Okay, it was listed at 301.6. So we actually overestimated what the population was going to be by about, so we overestimated by approximately 15.5 million. Okay? But that's how you do exponential regulation. Exponential regression, same situation. Enter your L1 and L2, use EXP reg, okay? Get your function, and then we're going to plug in 107 because in 2007 it had been 107 years since 1900, and then take your result and compare it to the listed result. So that's that. We're not going to do anything else. I know there's some slides in the notes, guys, that you're like, okay, what do we do with these? If we didn't go over it in this video, cross it out. Okay? Bye.